So last class discussed about the controllability, observability concept and also state transition matrix in the state space analysis in control system subject. Now we go for the state model from different situations, that is derive the state model from transfer function, derive the state model from electrical circuits, derive the state model from differential equations. So we go for the first one, derive the transfer function, derive the state model from the transfer function. So suppose they given the transfer function is y of s by u of s equal to s plus 4 by s square plus 6s s cube plus 6s square plus 11s plus 6. The given transfer function is y of s by u of s is equal to, so s plus 4 by s square s cube plus 6s square plus 11s plus 6. So now, so from this transfer function derive the state model. So first of all, so observe the highest degree of a given transfer function. So highest degree is nothing but that is the 3. So highest power of s is nothing but highest degree. So 3 is the degree. So now, so by divide the numerator and denominator, divide the numerator and denominator by divide by s cube. So that is s plus 4 by s cube divided by s cube plus 6s square plus 11s plus 6 by s cube. So therefore that is equal to 1 by s square plus 4 by s cube divided by 1 plus 6 by s plus 11 by s square plus 6 by s cube, and 1 by s square plus 4 by s cube, 1 minus half minus 6 by s minus 11 by s square minus 6 by s cube. So the denominator of this one will be reformed into like this. Now we have to look on the transfer function. So 1 by s square plus 4 by s cube, 1 minus half minus 6 by s minus 11 by s square minus 6 by s cube. So look like these two are the forward path 1, forward path 2, and this loop 1, loop 2, so like this loop 3. So look like as a, from this transfer function we can draw a signal flow graph. From that signal flow graph method, so we have to derive the state model of a system. So first of all, a signal flow graph indicates nothing but number of nodes. So this is u and this is y. So now on 1 and this is also 1. Now go for, so x1 bar, x2 bar, x3 bar, and this is u1. So now we have to identify the each and every path gain. So this is 1 by s and this is also 1 by s and this is also x1 bar 1 by s. So put 1 by s on x1 bar, x2 bar, x3 bar. So now the first forward path 4 by s cube. So now the first forward path is nothing but from input to output path. So this is like this 1 by s into 1, that is 1 by s cube. But our forward path is 4 by s cube. That's why put 4 in this one. So now the first forward path is 1 into 4 into 1 by s into 1 by s into 1 by s into 1, that is nothing but 4 by s cube. That is the first forward path is coming. And second forward path is 1 by s square, that is nothing but here 1 by s. So like this we have to, so this is 1. So u, from u 1 into 1 by s into 1 by, that is 1 by s square. Now the first two forward paths are constructed. Now go for the loops. So that is, this is y, and so from this x1 bar, so this is minus 6. So minus 6 by s minus 6 by s. This is the first loop, and second loop is x2 bar, and this is minus 11 by s square, and third loop is x3 bar. This is minus 6 by s cube. So this is the signal flow graph construction from the given transfer function. Now from this signal flow graph construction, we have to derive the state model of a system like this. So from the SFG, so y is equal to x1, that is nothing but here look like. So here, so this is x1 and this is y, 1, 1. So y is equal to x1. So y by x1 equal to 1, that is nothing but y is equal to x1. Take the equation 1. Taken as equation 1. So this is equation 1. So from x1 bar equal to, so from the SFG x1 bar equal to. Now identify how many paths are coming to the x1 bar. So here two terminals are there. One is x2 is coming to x1 bar, and minus 6y is coming to x1 bar, that is nothing but minus 6y plus x2. These two paths are coming to the x1 bar, that's why minus 6y plus x2, but y is nothing but x1, so that is nothing but minus 6x1 plus x2. This is equation 2. And next one, x2 bar. So this is x2 bar. How many paths are coming to the x2 bar is nothing but here minus 11y is coming, and also so x3 is coming, and also u is coming. So three variables are coming to the x2 bar, that's why minus 11y plus x3 plus u, 1u, that is nothing but minus 11x1 plus x3 plus u. This is equation 3. And last one is x3 bar. x3 bar, from this x3 bar how many paths are coming? Here only two paths are coming, minus 6y and 4u, that is minus 6y plus 4u, so that is equal to minus 6x1 plus 4u. So this is equation 4, right? Now from this equation 2, 3, 4, we have to write the matrix state model form. So x1 bar, x2 bar, x3 bar equal to, so and this one is x1, x2, x3, this is u. So from equation 2, 6x1 minus 6x1, that is minus 6, there is, and x2, that is 1, there is no x3 term 0, and there is no u term 0. And from equation 3, so minus 11, so there is no x2 term 0, and this is 1, and u term is there, that is 1. And from equation 4, minus 6x1 plus 4u, that is minus 6, so 0, 0, so and this is 4. So this is equation 5. And from equation 1, y is equal to 1, 0, 0, x1, x2, x3. This is equation 6. Now this is the state equation and this is the output equation. The equation 5 and 6 together called as state model of a given transfer function. Like this, we have to derive the state model from a given transfer function. So another problem is also there. So we have to observe another problem. So y of s by u of s is equal to 160 into s plus 4 by 160 into s plus 4 by s cube plus 8s square, s cube plus 8s square plus 192s 640 plus 640. This is the another problem. Now for this we have to determine the state model. So that is my, as usual, observe the highest degree of the given transfer function. Here s cube, that is 3 is the degree. So divide the numerator and denominator. Divide by s cube. So that is nothing but y of s by u of s is equal to, so 160s plus, so 640 divided by s cube, and also s cube plus 8s square plus 192s plus 640 divided by s cube. So like this, the value is 160 by s square plus 640 by s cube divided by, so 1 plus 8 by s, so 192 by s square plus 640 by s cube. And this transfer function may be rearranged as, so 160 by s square plus 640 by s cube, 1 minus of minus 8 by s minus 192 by s square minus 640 by s cube, like this. So for this transfer function must be remodeled as this one. This will look like as a transfer function. These two are the forward paths. So 640 by s cube and 160 by s square, and these three are the loops. 8 by s, 192 by s, and 640 by s. These three are the loops. From this transfer function, we have to construct the signal flow graph. From that signal flow graph, we have to derive the state model of a given system. So as usual, x1, x1 bar, x2 bar, x3 bar. In between the two, we have put 1 by s. So and also output is y and input is u. So this one, first one, 640 by s cube. So now in place of 4, we have to put 640 into 1 by s into 1 by s into 1 by s, that is nothing but 640 by s cube. Another one is 160 by s square. So this is 160. So 160 by s square. So two forward paths are available. Now coming to the loops, 8 by s, and this is minus. So this is 8 minus 8 by s minus 192 by s square, and also this is minus 640 by s cube. Like that, you have to construct the signal flow graph from the given transfer function. So now from that signal flow graph, derive the state model of a system. So this is y and this is x1. In between these two, so there is no gain. That is 1 is the gain. So y by x1 is equal to 1. So y by x1 equal to 1. So from this SFG, y is equal to x1, taken as equation 1, and now x1 bar equal to minus 8y plus x2. So that is minus 8x1 plus x2, and x2 bar is equal to, so here minus 192y plus x3 plus 160u. So that is minus 192x1 plus x3 plus 160u. So this is equation 3, and also from x3 bar equal to minus 640y plus 640u. So minus 640x1 minus 640u, minus 640x1 and also minus 640 plus 640u. So these are the taken as equation 2, equation 3, equation 4. Now from this equation 2, equation 3, equation 4, we have to observe we have to develop a state model of a system. So that is, so as usual, x1 bar, x2 bar, x3 bar equal to, in terms of x1, x2, x3, and also this is u. So from equation 2, minus 8x1 plus x2, that is minus 8, 1, 0, and u also 0. From equation 3, minus 192x1 plus x3, minus 192x1, there is no x2 term, that's why 0, and x3 term is there 1, and also u term is there, that is 160. So and last one, minus 640, 0, 0 640u. So this is equation 5, and from equation 1, so output y is equal to 1 0 0 x1 x2 x3. So this is equation 6. So equation 5 and 6 together called as state model of a given transfer function, like this. So we have to derive the state model from the given transfer function. Now another model, so they given differential equations. So determine the transfer function. So for that, go for the another problem. So they given a differential equation like this. So y triple dash plus 4y double dash five y dash plus 2y equal to 2u double dash 6u dash 2u double dash 6u dash plus 5u. Like this they given differential equation. Determine the state model of a system. So as usual, we know that the differential equation must be rearranged as d cube y by dt cube plus 4 d square y by dt square plus 5 dy by dt plus 2y equal to 2 du by dt, d square u by dt square plus 6 du by dt plus 5u. So apply the Laplace transforms. Apply Laplace transform on both sides. That is, so s cube into y of s plus 4s square into y of s plus 5s into y of s plus 2y of s equal to 2s square into u of s plus 6s into u of s plus 5u of s. So taking a common factor as y of s cube plus 4s square plus 5s plus 2 equal to, so 2s square plus 6s plus 5 into u of s, and now y of s by u of s is equal to, so 2s square plus 6s plus 5 divided by s cube plus 4s square plus 5s plus 2. So from this differential equation, first we have to apply the Laplace transform and then convert time domain into s domain. So rearrange that one, determine the transfer function. As we determine the transfer function, so similar manner. So last problem we have to do the transfer, from the transfer function we have to derive the state model in similar manner. So observe the highest degree, that is s cube. So divide the numerator and denominator with s cube. So and rearrange that one, that is, so 2 by s plus 6 by s square plus 5 by s cube divided by 1 minus of minus 4 by s minus 5 by s square minus 2 by s cube. So and this one may be arranged into, so as usual arrange it into as usual. So u, so this is u, this is 1, like this. So x1, x2, x3 as usual. x1, x1 bar, x2, x2 bar, x3, x3 bar, in between that one. So put a 1 by s. So and this is the transfer function output and the u is the transfer function input. Now first for 2 by s. 2 by s is not, sorry, first 5 by s cube. So put 5 into 1 by s into 1 by s into 1 by s, 5 by s cube, and second one 6 by s square. So this is 6 into 1 by s into 1 by s, 6 by s square, and last one 2 by s, that is nothing but, so another forward path. So this is 2, another forward path. First one is 5 by s cube, second forward path is 6 by s square, and third forward path is 2 by s. So upper part is over. Now go for the loops. So minus 2 by s cube. So sorry, minus 4 by s. So this is minus 4 by s minus 5 by s square, minus 5 by s square and 2 by s cube. This is the minus 2 by s cube, and this is the signal flow graph construction from the given differential equation. From this, y is equal to x1 and x1 bar is equal to minus 4y plus x2 plus 2u is there here, 2u. So therefore minus 4x1 plus x2 plus 2u, this is equation 2, and from that one x2 bar equal to, so minus 5y plus x3 plus 6u. So therefore, so minus 5x1 plus x3 plus 6u, this is equation 3, and last x3 bar equal to minus 2y plus 5u. So minus 2y plus 5u, so therefore minus 2x1 plus 5u. So this is equation 4. From that you have to construct the state model of a system. So that is x1 bar, x2 bar, x3 bar. So in terms of x1, x2, x3 state variables, and this is the input u. So from equation 2, so minus 4, 1, 0, 2. From equation 3, minus 5, there is no second term, that is x2 term, 0, 1, 6u. And equation 4, minus 2, there is no x2, x3 terms, 0, 0, and 5u. This is equation 5. And from equation 1, y is equal to, so 1, 0, 0, x1, x2, x3. This is the output equation. So equation 5 is the state equation, equation 6 is the output equation. So state equation and output equation together called as state model of a given differential equation. Like that, so we have to derive the state model from the transfer function and also differential equations. So next class we have derive the state model from electrical circuit also. So please subscribe the DBS Talks to see this video.